So we're covering sections 5.8 and 5.9 of Wessel's notes on spectral analysis and discrete power spectrums. I went through an introduction with some examples. I've reviewed periodic functions and discussed some key properties of these functions, including the orthogonality relationships between sines and cosines. And now let's talk about discrete Fourier series. So that'll be the topic of this video. So a complete Fourier series can be described, so a complete Fourier series for a continuous and infinite sequence is described by an infinite sum of sines and cosines. Okay, so that's our complete Fourier series. But of course, in practice, even with fast computers, we can't sum infinite numbers of functions, and our data sets are never continuous. So to deal with discrete series, we have to use an approximation, which is a finite sum. And I'm going to describe the approximation as y with a caret over it following Wessel's notations. And that's we have a coefficient, a zero, j equals 0 coefficient divided by 2 plus a sum of j equals 1 to our data record minus 1 divided by 2. And then again, we have our amplitude of our cosine function times the cosine function with frequency omega j for each point of t plus the amplitude of our sine function with a angular frequency of omega j, again at each point in time of our record. So here is we're summing over the different harmonics to get each value of y, or our approximate value of y, at each value of t, the ith value of t and y. Now the sum is up to n minus 1 over 2, and for simplicity, let's take n to be odd. So in this discussion, let's always have n as odd. If by chance you get a record in which n is even, it's easy enough just to remove the last record. So you can sacrifice one measurement for simplicity to make n odd. So if you subtract 1 from an odd number and divide by 2, you get an even integer, of course. Now the aim of Fourier analysis is to, so we're decomposing this function. So y is our true data, and it's approximately equal to this the sum of sines and cosine functions. And so the aim of Fourier analysis is to make this decomposition, and in doing so, we have to solve for these two coefficients. So this is our aim here. And again, if we return and look at our example again of our temperature in our borehole, we had a temperature variations as a function of time, and I showed you how we did this Fourier decomposition to produce this periodogram showing the amplitude of each harmonic component. And so these amplitudes are what we're solving for when we solve for AI, AJ, and BJ. And the number of coefficients is n minus 1 over 2 times 2, right? So we have n minus 1 over 2 values of A and n minus 1 over 2 values of B, and then plus we have 1 for the A0 value. And so that equals n coefficients. Now, we can already do this using generalized least squares. Right? We could define our vector of coefficients as A0, A1, all the way up to A n minus 1 over 2, and B1, B2, all the way up to B n minus 1 over 2. Okay, that would be our coefficient vector that we could solve for using general least squares. But this can take a lot of CPU time and RAM if n is large. So this is not very computationally efficient. For small problems, it's quick and easy, and we know how to do it, but I'd like to show you a much faster or efficient method. So this faster method exploits the orthogonality relations of sines and cosines that we just talked about. So let's consider an operation in which we sum over our data record each value of y, so this is our data value, times cosine times a cosine function. And that cosine function has is the kth harmonic that we're multiplying each value of y with. And here we're going to say that k is not equal to 0. K can be anything between 1 and n minus 1 over 2, but it cannot be 0. So let's write that out with y approximated by our sum of harmonic functions. So approximating y with a over 2 plus our sum over all our harmonics, and that's a sum over j. So everything in the curly brackets is our approximation for y at, again, at each point of I, at the ith point, and that's summed over I. And we're multiplying that again by cosine omega t I. Okay, so now let's look at this, this operation term by term. So our first term is the sum of a naught over 2 times cosine omega k ti, and that's equal to 0, right? If we sum a cosine function over over a discrete number of oscillations, we get 0. The area under the cosine function is 0. So let's look at our second term. Actually, let's look at our third term first. Our third term turns out to be the interesting one. And our third term, again, we're summing over our full record length, and we have a sum over each of our harmonics of bj sine omega j ti times our kth harmonic function. Okay, now we're just summing here, so we can certainly rearrange the order in which we do the sum. So I'm going to bring the sum over the j over j on the outside, do that last, and sum over our record first. And by doing so, you see that we have a product of a sine and a cosine function. And if we multiply a sine, any sine and any cosine function, and sum over an integer number of oscillations, then we're going to get 0 by the orthogonality of sines and cosine functions. So the third term turns out to be 0. So our first term is 0. Our third term gives us 0. And then finally, our second term, and I'm going to write that with the sum over j on the outside and the sum over our whole record length on the inside. Because this illustrates that we're really summing a product of two cosine functions. And remember, by the orthogonality relationships of cosine functions, when j is not equal to k, then we get 0. So again, we're summing over all the j harmonics, and the only term that remains is the term in which j is equal to k. The only term that gives a non-zero value is when j is equal to k. And this gives a k n over 2, right? The sum of the product of two cosine functions with the same periods over the whole data record was n over 2, and we're multiplying by a k. So we find that AK if we set this equal to the left-hand side here, we see that AK is equal to 2 over n times the sum over the data record of each of our data points times cosine omega k t I. And this gives the solution for AK. And again, AK is the amplitude of the cosine function for the kth harmonic. And Wessel goes through an analogous derivation, but he shows that this solution for AK turns out to be the solution that is the least squares solution. Okay, so it's a least squares solution, but it's done more simply than the general least squares inversion by just doing this one sum. It's done in a shorter way than the generalized least squares solution. And it turns out that the coefficient on the sine function, the kth coefficient for the sine function has a similar form, 2 over n times the sum of for I is equal to 1 to n of our data values of y times the kth harmonic for the sine function. Okay, and this is for, again, for k is equal to 1 to n minus 1 over 2. Right. So this is true for, again, k equals 1 to n minus 1 over 2. And likewise for the sine function. Now let's look at the 0th harmonic, B for the 0th sine harmonic. And if we use our same equation, we get yi times sine of 0. And that gives 0. So B0 is 0. And our 0th harmonic for the cosine part is yi cosine 0. And this is 1. So this is simply 2 times the mean value of y. We're just summing y over all its values and dividing by n, and that gives the mean value. So a over 2 is simply equal to the mean value of y. So when we go back and look at our decomposition, we see here that we have the mean value of y as our zero wave number or infinite period component. It's a constant component because you can visualize it as with zero oscillation. It has a period of infinity, which corresponds to a constant value, and that constant value is the mean value of y. The rest of the decomposition describes the variations about the mean. And again, I'd like to remind you that the angular frequency of the kth harmonic, that's omega k, is equal to 2 pi over the period of that harmonic, and that's equal to the length of the whole record, which is n delta t, that's the whole record length divided by k. Also, remember that the time of the ith record is equal to delta t times I, and therefore omega k ti is equal to 2 pi times I divided by n over k. And again, to remind you that the lowest frequency, the lowest angular frequency corresponds to the fundamental frequency, that's omega 1, and that's equal to 2 pi over n delta t, the length of the whole record, where t is the fundamental period. It's the longest period that can be resolved by the record. And the highest angular frequency in this case is omega n minus 1 divided by 2, and that's equal to 2 pi all over n minus 1 times 2 delta t. And this is almost the Nyquist frequency. Recall that for simplicity, we restricted ourselves to an odd data record. And with an odd data record, this is the highest frequency that we can describe. With an even number of records, number of measurements, we would reach the Nyquist frequency, and that is omega n over 2. And that's equal to 2 pi over 2 times delta t. Again, the shortest period that we can resolve is twice the sampling interval of our record. Okay, well, I guess that will conclude my discussion of discrete Fourier series. The next video will move on to the periodogram.